I'm super excited to be here to present an overview of Icechunk, this new open source transactional storage engine that we've been working on. I know that's a mouthful, so don't worry. I'm going to explain exactly what Icechunk is. I'm going to give you some live demos. I'm going to explain how it fits into our broader platform at EarthMover, and hopefully have plenty of time for questions and discussions from everyone who's here. So let me just dive into it first with a just short introduction to our company, EarthMover. So EarthMover is a public benefit corporation founded by myself and Joe Hammond. And our mission is to empower people to use scientific data to solve humanity's greatest challenges. And so I think what's unique about EarthMover is we've brought together folks like myself and Joe who have experience as practitioners in science, and leaders within the open source community, with folks who have built hardcore backend data infrastructure at some of the top tech companies in the world, such as Google, AWS, and Planet. And so with this sort of unique combination, we're really trying to advance the frontier of scientific data management in the cloud. And I think we made a big leap forward with Icechunk. We're excited to tell you about that today. Icechunk is sort of the latest iteration in our long-term leadership in open source. So Joe and I met working together on Xarray, where we were both core developers today. Xarray is a tool that many of us know and love for working with multidimensional array data in Python. And we've also spent many years prior to EarthMover working on Zarr, a storage format for multidimensional array data in the cloud. And so both of these dovetail really neatly with the Icechunk project. So here's an outline for what I'm going to be sharing today. I'm going to spend some time going over the overview, going over the sort of the status quo. How are we interacting with multidimensional array data in the cloud today? And what are some of the problems that we as a community are facing there? Then I'm going to start really with the impact. What does Icechunk allow you to do as a data scientist or a data engineer that you couldn't do before? Focusing on the transaction capability, data version control capability, virtualization of archival file formats, and then the performance results that we've seen from Icechunk. Having summarized what the impact is, then we're going to go look under the hood a little bit and talk about how Icechunk works. That's aimed a little bit more at developers. And finally, I'll spend a little bit of time at the end on the backstory about why we decided to create this new open source library and how it fits into our roadmap as a company. Okay, so part one, let's talk about the status quo, multidimensional array data in the cloud. First of all, what are multidimensional arrays? Some people like to call them tensors. I personally can't stand that terminology, but I've come to accept that it is out there in the world. Arrays are really a foundational data structure for computational science. And by arrays, I mean these hypercubes of 0, 1, 2, or 3, or even more dimensions that are used to hold sort of homogeneous pieces of data. These are ubiquitous throughout scientific and engineering applications. Of course, we use them heavily in geospatial data science to represent data cubes, model simulations, but they're used in many other fields of science and engineering as well, heavily in bioinformatics and microimaging. They're, of course, fundamental for deep learning, where the tensor terminology has really stuck. So the way we represent neural network weights and states of such a neural network are through tensors. And they're used throughout simulation. So if you want to simulate what's going on inside a fusion reactor, you will be encountering a lot of multidimensional array data structures. So just to sort of set the stage. Now, these domains of science have strong links to traditional high-performance computing. This is where I got my start as a computational science, by running ocean models on big supercomputers. And so the use of arrays as a storage format and as a data structure in this type of scientific simulation is really ubiquitous, where we often find HDF5 or NetCDF4 files as sort of the standard today. These simulations rely on the presence of a large shared file system. So a big shared disk that all of the compute nodes can read and write to. And the workflow for this environment often involves a simulation that will spit out many files, and then those are sort of passed on to users to analyze and eventually archive to tape. Now, today we're seeing a big migration of data and analysis and machine learning workflows to the cloud. And what we've seen is that this approach to data doesn't work that great in a cloud computing context. And the main reason for that is that in cloud, our shared storage is object storage, not file storage. And that means that data are read and written via relatively high latency HTTP calls rather than those fast operating system calls of shared file systems. So the archival file formats designed around those file systems either don't work at all in the cloud or have very poor performance characteristics with object storage. And this is a problem that our community, the Pangeo community, has been wrestling with for quite a while. This is a 6-year-old blog post from Matt Rocklin identifying the challenges of trying to work with HDF files in the cloud. And so a really exciting technology that's emerged in response to this challenge is Zarr. Quick show of hands. Are you guys able to raise hands? Who here actually uses Zarr? Okay, bunch of hands popping up. Wow. Okay, that really works. So we got folks on the call who are familiar with Zarr, right? Zarr is an open source cloud native format for multidimensional arrays. And it really places no limit on the size of the arrays we can store. It enables us to read and write those arrays in parallel, and it's quite scalable with object storage. And so these are some of the reasons why Zarr has taken off as a solution. And just a little bit of how Zarr actually works. Zarr is extremely simple. It basically just stores metadata in JSON files and then stores chunk data, the actual binary data, using this schema of keys that are then dumped directly into storage. And so it's spreading the state of our Zarr data set over many different objects in object storage. So I love Zarr. I've been using it for many years. Joe and I implemented the original integration between Xarray and Zarr. And having said that, I've come to realize that there's some real kind of problems with how Zarr works, particularly when it's being used in this sort of multiplayer context in the cloud, where we have multiple different users or processes that are accessing the same Zarr data at the same time, and particularly writing that data. In short, Zarr works great if you create it once and you never update it again. But once you have to update it, and by update I include the process of appending or extending Zarr data sets, you get into the situation where it's not consistent from a database point of view. What I'm showing on this slide is a scenario where one user starts writing a big update to the Zarr data set. Another user comes in and reads in the middle of that. And then later on that update finishes. It's really ambiguous what user B here is actually going to see. They might see data that's in an incorrect or incomplete or potentially even broken state. And that turns out to be a deal breaker for folks who want to use Zarr in a more production context as opposed to just kind of a low stakes research context. And those are precisely the sort of customers we've been working with in Earthmover, folks who really want to rely on this data as a database. This issue really stems from the fact that Zarr is not actually a file format like HDF or TIFF, but actually a whole directory structure that's spread over many files. And so it's kind of like a database, but it doesn't offer all of the database style primitives and that you would expect. Now, within this landscape, we see large data providers adopting cloud as a means of distributing data. Two prominent examples in our community are the NOAA Open Data Dissemination Program and the NASA Earth Data Cloud, right? But for the most part, they are moving existing file archives to object storage without really rethinking the data architecture. So I'm characterizing this as a lift and shift effort. And as a result, the cloud is frequently being used more like a big FTP server rather than truly taking advantage of the sort of more cloud native access patterns and workflows that are possible. And I think that's understandable, particularly given some of the challenges that I just described about using Zarr in a production context. Now, these archival file formats have a lot of data gravity associated with them. So here are two projections about the volume of data that's going to be generated and stored by NOAA and NASA's Earth science data programs over the next decade. And you can see we're measuring this data volume in exabytes, right? And almost none of this is Zarr. It's all NetCDF, GRIB, and TIFF for the most part. And so irrespective of whether we should use Zarr or not, this data exists. And there's a huge interest in leveraging it as is without having to rewrite the data. And that's where another exciting sort of existing technology comes in, which is the Icechunk / virtualizar approach. Another show of hands for folks on the call who have used either of these technologies. Yeah, so this is a little bit more new, but it's really exciting. The idea is that we can virtually map the contents of those HDF or NetCDF files to the Zarr data model, sort of by scanning them and building an index. And that allows us to sort of retroactively cloud optimize all of this archival data. Now, that's not a perfect solution. There's still some trade-offs that come with that. And as folks who do this know, what's actually inside those files matters a lot. And there's a lot of variance in terms of chunking and compression. There's also another problem that's created by this approach, which is you have to now keep track of these so-called references that you generate from this approach. So, you need to store them somehow in some kind of database. So again, we sort of bump up against database type questions and problems. So to sort of summarize my view of sort of the status quo, prior to 2 weeks ago when we dropped Icechunk, we've got these archival array file formats, which are really not designed for cloud object storage, and as a result are kind of slow. We're producing data at a massive rate still in those archival formats. Folks who have the option to use Zarr are choosing it and like it, but are still coming up against some limitations. Of course, you generally have to transform data to Zarr. Not a lot of data is originating in Zarr. And then there are these consistency issues around multiplayer mode, and that can make it feel a little fragile to use in a production context. And so, and then finally, we have this Icechunk and virtualizar, approach, which seems to have a huge potential to retroactively optimize these existing archives, but we haven't really seen this get put into production yet. It's mostly in the form of sort of third parties, people doing this experimentally. And so we'd love to see that be established as a really production grade practice, but we don't seem to be there yet. So we think we can kind of fix a lot of these problems in one go through the Icechunk project. Okay, so Icechunk is our new open source cloud native transactional tensor storage engine. Okay, again, it's a mouthful. I'm going to walk you through exactly what it is and how it works, and explain how it helps us overcome a lot of these challenges. Okay, so just in terms of Icechunk 101, you can go check it out at icechunk.io, and we have the GitHub repo up on GitHub. So as I said, Icechunk is a transactional cloud-native storage engine for Zarr. So it's not a standalone library or a completely new format. It's designed to work together with Zarr, particularly Zarr Python 3 currently as implemented, although we recently learned that it's been implemented in the Rust Zarr library as well. So through that compatibility with Zarr Python, it is also compatible with Xarray and virtualizar, which I've spelled wrong here, modulo a few in-flight pull requests that are required to get everything wired together. Now, the core of Icechunk is implemented in Rust, and there's just a thin Python wrapper on top, and it's 100% open source, licensed under Apache 2.0. So what is Icechunk? What does it do? Well, first of all, let's start with what you can store in an Icechunk repo. An Icechunk repo acts like a Zarr store, right? And so Within that, you can store anything that Zarr can store. You can use groups, you can use arrays, you can store metadata for both of those things. You can have infinitely, well, not infinitely, you can have deep hierarchies, and you can choose chunking and compression as you would already do if you're a knowledgeable Zarr user. However, the big difference is there's also this sort of system of snapshots that allows this repository to evolve over time in a safe way. So whenever you're viewing the state of an Icechunk repo, you're doing it in the context of a particular snapshot. And so here I've just tried to illustrate this by showing a timeline of how we might, build up a data set over time. We'll initialize an Icechunk repo. We'll add some data. We'll write to those arrays. We might make some corrections. And each of those updates generates what we call a snapshot. And this is what allows Icechunk to be safe and by implementing this sort of database concept of transactions. Rather than just pushing all of these changes immediately, they're staged and they're propagated in an atomic update. Get much more into this in the demos, but this is just kind of at the high level. Now, what do I mean by storage engine? Well, this is kind of, how our stack looks today. Essentially, if you're using Zarr in the cloud, you're using it together with the fspec library. And so as in terms of a software stack, you've got Zarr talking to fspec talking to object storage. And fspec is, responsible for figuring out how to talk to S3 or Google Cloud Storage. But it's basically just passing the Zarr keys through unchanged. If I set a document of this name from Zarr, fspec just goes and reads or writes that thing directly on object storage. So in the Icechunk architecture, Icechunk is replacing fspec here. You're still using the Zarr library, but Icechunk is now doing more with, in between Zarr and object storage. In particular, it is sort of taking those raw key values that come from Zarr, and it's translating it into the Icechunk storage specification, which is different from just the plain straight up Zarr one. And this is how it achieves all of the things that it's able to do while still remaining fundamentally interoperable with Zarr. So this is what we mean by a storage engine for Zarr. You drop it in underneath Zarr. You give Icechunk the job of getting and setting data in object storage, and it then provides you with many benefits: transactions, data version control, and also, as we'll see, some big performance boosts. So let's dive into that impact. What does Icechunk enable? What does it allow you to do that is hard or impossible with regular non-Icechunk Zarr? Well, one of the ones that I like to start with is this idea of multiplayer mode. One thing that's been really cool to see with Zarr is how organizations of all sizes are creating these large Zarr stores in the cloud and then using that as a sort of central database for all kinds of different processes that depend on that data. It's a great pattern. It enables all kinds of efficiencies in the data system. However, because of the consistency issues I mentioned, there's risk of users seeing data in an inconsistent state or an incomplete state when you're updating data. So with Icechunk, all updates to data sets occur within a transaction and create a new snapshot of the data set. And these snapshots are always occur in a specific order that all readers of the data set can agree on. This is a term from database systems called serializable isolation, the highest level of isolation guarantee that database systems can make. Readers only ever see one of those snapshots. They never see the intermediate in-between state while data are being written. But still, there are no locks required for either reading or writing data. You can always open and access the data at some snapshot. And then there's an optimistic concurrency control system for detecting and resolving write conflicts if they do occur. So this is some technical database talk, but overall the point here is that these features make Zarr work more like a database. Okay, so I'm going to show you this now through a demo. So I am now going to show you some notebooks, and this is a notebook this is actually 2 notebooks that I'm going to run in parallel that demonstrate interacting with an Icechunk store from 2 different uncoordinated sessions. And so I'm not going to try to live code here, but I am going to walk you through these notebooks in the proper sequence. And I think this will illustrate the power of Icechunk pretty effectively. So let me start from this notebook here on the left. This is going to be player A. And then over here, I've got player B. And I'm going to execute these cells in a specific order to simulate a sort of collaborative workflow here. So let me start by this notebook. And here I'm going to initialize a new Icechunk store. So I'm going to create a new store, and I'm going to configure that with my S3 credentials in my environment in a particular bucket and a particular path within that bucket. So this is how you set up an Icechunk store. And once we do that, we can just create a Zarr array directly in that store by pointing the Zarr at that store. So we've created an Icechunk store. We've written some data to it. So this is like 10 million values of data. And then we're just going to make a commit. Okay, so this should all look pretty familiar if you're used to using Zarr, but the new thing is this commit part, right? The commit is what seals this transaction and creates the snapshot that now other readers of the data set will be able to see. So now let's go over to player B. And we're going to open that existing repo, and we're going to read some data back. And if we look at the ancestry of this store, we can see that we see the same snapshot ID from both sessions. So we know what snapshot we're on. Now, what I'm going to do over from B is update some data. So I'm going to take a particular point, and I'm going to write a new value to it. I'm going to overwrite some data. And I'm going to commit that change. Okay. Now I'm going to go over to player A and try and do the same thing and write a different value. Okay. And what we're going to see is an error. This is a very good error. This is an error we want to see. This is telling us that we cannot commit this transaction because somebody else committed something that's in conflict with it first. So this is the Icechunk system preventing us from corrupting our data. Now, if we want to move past this, we can retry the operation on top of the latest data. And I'll note this is truly safe to a race condition. Here I have a lot of spacing between writing one and writing the other. But even if we tried to make both of these updates happen at the exact same instant, only one of them would succeed. Now, what I'll do over here is from A is I'll check out the data again. I'll sort of reset my state. I'll check out my main branch, and I'll write the data again. And now, finally, this commit is allowed to succeed because it happens in the proper serializable order. Now let's make another change over here. And let's pretend we're doing an expensive, slow operation. So I'm going to resize this array to be twice as large as it was before and write some new data to the new portion of the array. So let's pretend this takes a while to run. It's a big, expensive, complicated update. We'll go back over to player B, and we'll check out the store. Now, no new snapshot has been committed, so I don't see that change in size. And if I look at an element of the array, I can see the previous values that are written. None of the changes that are happening over here with A that are still uncommitted are going to be visible to B. Finally, I'm going to commit from A and then look for these changes in B, and I'll be able to see the changes that were made by A. So this is just illustrating this sort of multiplayer safety that is provided by Icechunk. There's no chance that you will ever see a write that's in progress. You'll only ever see a committed snapshot. And what this means is that you can really rely on these Zarr stores in production, even as you are updating them and changing them. And that's a core goal here. I'll just show now what this history looks like. We created 5 different snapshots along the way. can see they each have a timestamp and they each have a commit message and a unique ID associated with each commit. To finish off this demo, I'm just going to remove those files I created, and this will give you some idea of what the on-disk file structure is like for Icechunk. I'm going to dive into this more later on in the webinar, but you can see this is not your standard Zarr data. We don't see any chunks named 0.1 or this type of metadata, .json. We're using the Icechunk schema, which relies heavily on unique IDs to avoid collisions between different concurrent write processes. So we'll come back to this later. Okay, so now I'm going to go back to my slides here. So this is just sort of visual illustration of what I just showed. The way Icechunk works is you have a serializable history of snapshots that guarantee all readers will see the exact same thing when they write data. With this capability brings a bunch of exciting possibilities for data version control. So here I just emphasized the ability to make these safe updates. However, we can use these snapshots to do all kinds of interesting things. So here's an example of what I mean by data version control. So what I showed you just there, we were always looking at what we call the main branch of this data set, which sort of represents the latest update on a branch called main, or the latest snapshot. Icechunk also supports the concept of tags. So I can assign a tag to any snapshot, and those tags are immutable. And so tags allow us to sort of tag the state of a data set at some particular point in time and share something with folks that we know will never change unless we go and we delete the whole thing, of course. And so tags are perfect for a sort of reproducibility context. If I wanted to make a DOI and point it to some Icechunk data, I would point it to a specific tag. You can think of it as an immutable pointer to a snapshot. Other thing we can do is create branches. So say we want to start exploring and prototyping some changes to our data set, but we don't want those changes to be seen by the production process. We can make a new branch. Here I've called it dev. We can make new commits and evolve the data set on that branch. And then when we're ready to update, we can update this main branch pointer to be where the dev branch was when we're ready, say once we finish our quality control process. No, we do not have merging yet, but that's something we could explore in the future for the format. So I have another demo here for version control that will just quickly illustrate some of these capabilities. I'm just going to run through some of these cells quickly and illustrate some of the things that I just showed you in code. So we'll create a new Icechunk store here. We're calling this one webinar demo, version control demo. And just like before, I'm going to create an array, write some data to it, and make a commit. So this is an array with 10 million elements and 1 million chunks, data type I4. Now, I've got a commit ID that came out of that, and I'm just going to make a tag right now for that commit ID. That means we'll always be able to return to that state by referencing this tag. Now I'm going to make sure I'm on the main branch and then create a new branch called dev. So now I've sort of created a new branch off of main, and I'm going to make some changes to that. Say I'm going to overwrite all the data, set everything to -1, right? Okay. So now I'm just going to show how you can return to some of these other states of the data. So first I'm going to try checking out that tag. So I'll check out my tag and pull out a value from the array. I can see I've got what it was originally. I'll go back to the main branch, check out a value from that array. Same thing. It's actually pointing to the same snapshot as the tag. But I'll go to my dev branch, and I'm going to see the new data I've written here. Finally, on the dev branch, I'm going to make some more changes. I'm going to add some metadata. And I'm going to now bring my main branch up to date with the dev branch by calling reset branch. And I can see if I look at that array, I can see those attributes that I've just created. So, you know, if you've used Git before, some of these semantics will sound familiar. You're creating a tag, you're creating a branch, you're resetting a branch pointer, etc. It's nowhere near as rich and complex as the Git model, but the core concept of sort of snapshot / commit, tag, and branch should be familiar. And so, you know, we've just started to scratch the surface of what's possible here. There's so many cool things that this enables. You know, a big one that I have in mind is the sort of dev staging prod style separation of data within a single Zarr store, right? You can, if you have a data set that you're updating, you can actually have different versions of that you can, you know, evolve separately, do QA on, and then finally, when you're ready to, you know, merge to prod, you can do that. And so this is pretty exciting to me. I am going to now clean this one up. And as you'll see, you know, just to get a sense of some of the metadata files here, we created a tag file, and then we have multiple branches. We've got branch.main, branch dev. So these are all part of the Icechunk schema, how the data are actually stored internally, which we will get into soon. A word about virtual data sets. So virtual data sets are another key capability of Icechunk. The reason that you know, virtual data sets are easily supported in Icechunk is that all chunks in Icechunk are what we would call references. The system explicitly tracks every chunk that is written in metadata files, including the key, the offset, and the size. So with that architecture, it's quite trivial to add support for virtual chunks, which are just chunks that live in some other files outside of this store's hierarchy. Efficient storage and parsing of chunk manifests is really core to the Icechunk format. We need this capability for Icechunk to work. This happens to be a problem that sort of the Kerchunk and virtualizar community is very interested in at the moment as these sort of virtual data sets grow in size. If you're storing millions and millions of references, you know, it becomes important doing that in an efficient and scalable way. And so this is sort of a core goal of the project. From a reader's point of view, reading virtual data sets is indistinguishable from native data sets. Reading those data sets, you don't even know as a user that you're using a virtual data set as opposed to a native data set. And those virtual data sets can be incrementally updated or overwritten with native chunks, one chunk at a time. So the cool use case there is you could start with a virtual data set pointing to some existing data, and then you could incrementally change the metadata, add new metadata, update some of the variables, update some coordinates, and evolve those data sets up until the point where maybe you're no longer even, you know, pointing at the original file, but that's the way you started. I will now go to my next demo here with virtual data sets. I'm going to cheat a little bit on this one and just reference our documentation, since this is a more involved demo that will take longer to run through and share. I will just show you, this is also a good chance to show off the Icechunk documentation. We have a whole page on creating virtual data sets. I do want to note that doing this today involves unreleased versions and branches of multiple libraries, right? So we're sort of still wiring everything together to make sure that this works fully with virtualizar and Xarray. But I'll just walk you through what you can
merge support in virtualizar while you were talking. So if you reload this page, then there's one fewer dependency since you started talking.
Really? Oh, yeah. Love it. Okay, great. Progress happening literally during the webinar. This is great. You know, the basic process is fairly straightforward. In this example, we've got, you know, a bunch of netcdf files that are in S3 somewhere. This demo uses the NOAA CDR OISST data set, and it's got one netcdf file per day. We use virtualize-R to open those data sets in a sequence. Then we concatenate them using X-array. This is still magic to me that this syntax actually works, but this shows the power of virtualize-R for manipulating these so-called chunk references. And then we set up an Icechunk repo, a store where we can store these references into. There's some configuration overhead to get this working with, there's a couple different S3 buckets involved. There's the one where the references live. There's the one where we're writing the Icechunk store, etc. But storing this to Icechunk is a one-liner. Once we've got that, we can just open it with Zarr, open it with X-array, and explore the data and plot data from the virtual data set. It works. It's moving towards being fully supported within those libraries, and we are really excited about the potential here. Okay. I'm going to have to speed up if we're going to have some questions, because there's a lot of good questions in the chat. We've got 20 minutes left. And so I'm going to make a call to go kind of quickly through some of the rest of my material, because I really want to talk to you guys and get some feedback, and I want to prioritize that. So last sort of impact slide is about performance. We didn't optimize Icechunk for performance yet. What we have done is designed what we think is a good design, and we've implemented Icechunk in Rust. And we have been really excited to see that just those two ingredients are already delivering some pretty transformative performance results, particularly in terms of read throughput, right? And so what is shown here is the rate of fetching data from object storage using a range of different software stacks. And the units are gigabits per second. The network connection on this EC2 instance is about 10 gigabits per second. So that's the fastest we could ever read data from. Starting down from H5 NetCDF, we see we're getting really, really slow throughput, not pulling data fast at all. Now, as folks are already familiar, bringing in Zarr and Zarr version 2 with Dask can speed that up a lot, delivering a 10x boost. This is why people already like Zarr. Just skipping to the chase, bringing Icechunk in now on top of this, and also using Zarr 3, the latest release of Zarr, we're able to get throughputs exceeding 7 gigabits per second, more than 2x what the stack without Icechunk can do. And we don't fully understand actually why it's so fast, but these have been replicated by other users, and ultimately we attribute it to Rust just having a more efficient and scalable I/O stack than Python. So there's more work to do there, and I'm going to skip the demo where I actually show this off for you, but you can go read about it there's notebooks in GitHub where you can do them yourself. So let me get into the third part of my talk, which is how does Icechunk work? And again, I'm going to try to jump through some of this pretty quickly so we can have time for some discussion. Icechunk was directly inspired by something called Apache Iceberg. Show of hands, not if you've heard of Iceberg, but if you have actually read or written an Iceberg table. So Iceberg is what's called an open table format. It is a framework for organizing basically many Parquet files into a single logical table that looks and feels like a database, but is just stored on object storage. And so Iceberg does this through clever usage of metadata files that track the actual data files that are being written and read. Iceberg is really taking off as an industry standard. It's being adopted by all of the major cloud data platforms, Databricks, Snowflake, Google, BigQuery, et cetera, are all sort of converging on this as a industry standard. We can't use Icechunk directly for Zarr data, however, because it's really firmly married to the tabular data model, whereas we want to use the multidimensional array data model. So we wrote down some requirements that we wanted to satisfy in our design of Icechunk. First and foremost, we wanted it to be designed around the performance characteristics of object storage and leverage only object storage without having to rely on an external database or catalog or some other synchronization point. This concept of serializable isolation is really key to the design and was a core requirement. We wanted to be able to travel in time back to previous snapshots of our repositories after they'd already been written. A key requirement that is really what made us need to design a new format is the idea that to support these references. Supporting references to chunks in other external files is a pretty unique and particular thing that our community has started doing. We think it has a lot of promise, and so that was core to the design of Icechunk. And then finally, we wanted it to be easy to evolve the so-called schema, change the structure of arrays and groups within a store without having to rewrite or move large volumes of data, as you currently have to do with Zarr, right? If you want to rename an array, you actually have to copy all of its chunks to a new location in storage. And so we've surveyed everything that's out there, everything we could get our hands on in terms of technologies in this space. So we looked at all of the array formats, HDF5, NetCDF, of course, Zarr, Cloud Optimized GeoTIFF, TileDB embedded, safe tensors. We looked at every technology we could find. We also looked at all of these tabular formats. We realized we couldn't store array data, multidimensional array data natively in tabular formats. However, there's a lot of really smart engineering and innovation that's happened there. And so we studied all of those. And we looked at other related technologies in this space, such as LakeFS and TensorStore. And so we found a lot of great ideas out there, a lot of inspiration, but nothing that would check all of the boxes in our requirements. So we actually wrote all this down on our documentation page. We have a whole section on how does Icechunk compare to X. So I've seen a lot of questions already come through in the chat about how does this compare to this or that. Ian, I see your hand. I think we're going to do questions at the end. But if you want to know the answer to that, I encourage you to go check out this website. We've tried to answer all of what we thought would be the most common questions about how does Icechunk compare to X on this page. So here's the actual internal structure of an Icechunk data set. And so it starts from these what we call reference files, which are sort of these branch pointers that identify a particular branch name like main or dev or a tag. Those point to what we call snapshot files. So snapshot files are metadata files. You can think of them as like consolidated metadata files for Zarr, if you're familiar with that concept. They contain all of the metadata about the different arrays and groups in the store. And they also contain links or pointers to these so-called chunk manifests. So chunk manifests are essentially metadata files that tell us exactly what chunks are stored in that particular version of an array for that snapshot. And those finally are pointing at the underlying files in object storage where the chunk data live, or in the case of virtual data sets, to the NetCDF or HDF files where those chunks might be stored in. And so the process of creating a new snapshot in Icechunk looks something like this. A client starts, and here I'm just going to say client as like the user, the process that is creating the snapshot. And don't overread too much into that word client here, okay? The client writes chunk files eagerly as they would do with normal Zarr, except instead of storing them under deterministic file names, each chunk is stored under a random unique ID. Once the chunk files have been written, the client creates a new snapshot file and optionally chunk manifest files that are pointing to those chunks. So it creates these metadata files, again, using unique IDs. And then finally, the client updates a branch pointer by writing the next file in a predetermined sequence. And this is the point where we can actually detect and prevent conflicts between concurrent updates. Up until this point, everything has been written using unique random IDs to avoid any potential collision between conflicting writes. But at this branch update step, this is where we can detect and potentially stop a conflict between inconsistent updates, and eventually also retry that update if appropriate. So this capability depends on a object store primitive called a conditional write. And here's an example of, here's an announcement from AWS that came out as we were designing and building Icechunk this summer. So this idea that you can do a conditional write on object storage is actually really, really key for building consistent data systems. It allows us to use the object store's consistency properties to eliminate race conditions, rather than having to use some external locking mechanism. So this is this subtle technical update from AWS that was actually transformative for Icechunk and should be so for many other projects. I believe that if this had existed when Apache Iceberg had first been developed, for example, they wouldn't have needed an external catalog to make the format work. Just zooming out a little bit more, we see this as really part of a broader trend in the tech industry, which is to leverage object storage as a universal infrastructure backend, make object storage do as much work as possible to make the downstream library's job as easy as possible. I'm going to zoom over this. We wrote Icechunk in Rust, so it would be fast and correct. We have a Python layer on top of it, and actually this has also already been implemented in the Zarr's Rust crate. So those are the two Zarr implementations that support Icechunk. You can read a bunch about our roadmap online. We still have plenty to do, and I want to be very clear about stating that we haven't stabilized the format yet. We're still iterating on some details about how we store these chunk manifests. And until we do that, we can't recommend that you use Icechunk in a production context, because we don't know that where the format ends up is going to be backwards compatible with where it is today in terms of the on-disk format. So evaluate it, play with it, give us the feedback. Don't start using Icechunk tomorrow in your production system. We hope to be there very soon. I want to end just by talking a little bit about the backstory behind Icechunk. So you can go find a 2-year-old GitHub issue that I closed last week, essentially proposing this idea of doing something like Apache Iceberg for Zarr data. And that was open for a long time. And we went on this sort of very roundabout path to getting there, which is in our Array Lake platform at Earthmover, we implemented something very, very much like this in our first version of the platform. We essentially built a separate metadata store for Zarr data, where we take the user's data and we split the metadata all out into our backend database and store the chunks using this same sort of random UID scheme in object storage. And so I'm really glad that we did this, because we got a lot of experience in figuring out all of the sort of technical concepts around a transactional version-controlled Zarr store. And we got a lot of great feedback from our customers about this. And what we realized after having supported this for a while is that we could make this all a lot simpler by evolving this system to rely purely on object storage. So that's exactly what we did. The first version of our platform looked like this. It was really focused on those data governance features. This is what we call Array Lake. It includes some of the features that I described in Icechunk, such as these sort of transactional version-controlled updates on data, and also a bunch of other stuff: data catalog, metadata search, access controls, and a lot of convenience for teams working with Zarr data in production. We're evolving our platform today to go far beyond just that core data governance solution to include two other major components, one of which is a data ingestion engine that makes it way easier to pull in data from common sources and data providers into your data lake in the cloud. And then on the other end of that, what we call our query engine, which re-exposes that data through a range of common protocols such as OGC EDR, OpenDAP, WMS, that make it really easy to integrate that data with all kinds of downstream applications. And in the process, we've decided to open source the core data storage format in the form of Icechunk to benefit our customers and to benefit the broader Earth data science community. Our vision at EarthMover is really to enable the creation of what we call a planetary scale data federation in the cloud. We think empowering folks to exchange data across all kinds of different types of organizations, from academia to government to this rapidly growing private sector around climate and Earth system resilience, is going to empower reproducible open science and accelerate climate change solutions. So that's what we're trying to do as a company. If that sounds appealing to you, love to talk to you more about our platform, and don't hesitate to reach out. We have some time for questions, and so let's move into the Q&A with a few minutes left. And if folks want to stay on for another minute or two at the end of the hour, I'd be happy to do so. Andy Ryan asks, is there a way to prune old snapshots to save storage costs, e.g. remove old commits? Yes. So we need this in Icechunk for the format to be sustainable. We call this process garbage collection. And this is common to all database systems that use this type of architecture. We have not implemented the garbage collection yet. And so it's another one of those features that absolutely needed for the stable release. But it is, a straightforward process of identifying things that are no longer referenced within the store hierarchy and going and deleting those files. So that's one of these utility operations that's on our roadmap. Garbage collection absolutely will be implemented, not implemented today. Takaya asks, when you create a branch of data in Icechunk, what happens with the actual storage? If you have a main and dev branch, does this take up twice as much storage? Thank you for the softball question, Takaya. This is one of the beautiful things about Icechunk, is it really allows you to have this versioning in a very efficient way by just storing references to the chunks, right? We never duplicate chunks unnecessarily. So if you create a new branch that's referencing that's referencing existing data, we absolutely don't create any duplication of the chunks. There are a few new metadata files, and those are very small. If you start to overwrite the chunk data from that other branch, then yes, the storage will grow. And at some point, if you have two completely different versions of the same data where the actual values are differing, then yes, you have increased your storage footprint. But it is incremental. Okay, Riley, what's next for EarthMover? You guys open source an extraordinary fundamental piece of your product. What are you hoping to have as your core value add as a SaaS company moving forward? Wow, Riley, are you an investor? This is a hard question here. No, so I think I tried to address that in my slide here.
Yeah, I was typing that up right as you were showing this last slide. I'm really stoked about this, and it's super generous. And yeah, as somebody in the private sector now, I'm curious. You guys must have grand plans if you open source this, and I'm just curious what you're excited about bringing to the table on top of this awesome engine.
Our vision is to really just solve a lot of these hard yet semi-generic problems that we see folks having to build and maintain on their own in building Earth system data science workflows in the cloud. And so that the two main areas we've identified there are on bringing data in, and then on getting data back out and helping it to interoperate with existing applications, visualization, etc. So it's a great question. Okay, Henry asks, what is the difference between Icechunk and using DVC with Zarr for data version control? That's a great question. DVC, data version control, we should add this in our how does Icechunk compare to X. Fundamentally, DVC and other versioning system things like Git LFS or I would put LakeFS in this category as well. They're generic and agnostic to the underlying file format. So yes, you can version, anything that'll allow you to version control files. You can hypothetically version control Zarr data. By building a version control system specifically around the Zarr data model, that allows us to make certain optimizations and know, for example, that a metadata file is actually referencing, various chunks, that there are relationships between these entities. And so I believe that allows us to get better performance, more efficient use of storage, and a better user experience than any tool that's designed just for generic versioning of files. Okay, Riley's got some other popular ones here. Curious how seamless this is for integrating for legacy existing stores. I'm sure many of us have expansive data lakes with lots of Zarr data sets stored. So yeah, the process for adopting Icechunk on top of existing Zarr is to use virtualization. In this case, you are making a virtual Zarr from your previous Zarr data. So this is already supported in virtualized Zarr, but you can open those Zarr data sets and you can write them as references to an Icechunk data set. The one catch is that going forward, you need to commit to updating the data set through Icechunk. You can't go back and then update the reference Zarr data set. You have to kind of consider that now frozen and deprecated and evolve it on top of the new data set. We should put a page about that in our docs. That's a great question. Is a workflow seamless with Xarray? Yes. Maybe someone in the chat can put a link to that Zarr Xarray docs. Okay, I've been reading a lot of stuff. I see some folks with hands up, so I'm going to stop reading the questions. And whoever just has your hand up, let's see. I don't see a list of who has the hand up. Tim, go ahead, Tim. Why don't you ask a question live?
Hey, thanks, Ryan. Thanks for this great presentation. This was a follow-up to the legacy Zarr stores. If you use Icechunk in this way, do you get like the performance of Zarr v3 with Zarr v2 basically, and with everything that Icechunk has to offer too?
It's a great question. So you can read. I didn't mean to unshare. I know we reached the end of the hour, so no worries if folks have to drop off. If you're psyched to stay on, let's keep talking. First of all, you can read Zarr v2 data with the Zarr Python 3 library. This is a little bit confusing. There's two versions. There's the format version, and then there's the library version. Zarr Python 3 is about to come out, and period is going to be way faster than Zarr Python 2, particularly if you want to use it without Dask, because the new version of Zarr is async all the way through and has its own multi-threaded chunk decompression pipeline. So just upgrading to Zarr v3, something that our CTO, Joe Hammond, has been leading the development of, is going to bring performance benefits. If you want to use Icechunk on top of that, you can do that using the virtualization method that I mentioned, and that does require you to use Zarr Python 3 as well.
Thanks. That clears a lot up.
Yeah. There's a lot of moving pieces in this whole situation. So, anyone else feeling brave and just want to ask their question live?
Can I ask a question? Okay, this is Hailiang. Just like I know, like there's some effort before for rechunking, like it's called rechunker, right? So they have some very smart way to have some intermediate storage for that. If I use Icechunk to do the rechunking, will that take advantage of those kind of like algorithms?
I would consider these orthogonal right now. Rechunking is a generic process of transforming the chunks from one array to a different chunk shape. You can rechunk Icechunk data. You can store rechunked data in Icechunk. And other than the general performance benefits of reading and writing data faster, there's no particular advantage to using rechunker with Icechunk today. Let's see. Dumai asked about merging branches, not yet a feature. What might be the timeline for that? It depends on what you mean by merging branches. That's the short answer. There's various flavors of merging, some of which are very simple, some of which are very complicated. Let's go Max and then Alden.
Thanks, Ryan, for the webinar and open sourcing the tool. I was wondering if you can speak to the implications of relying on conditional rights for using Icechunk with other cloud providers.
We researched this before deciding to depend on that capability. AWS S3 was the only object store that did not support this up until August 20th. Every other object store, Google Cloud, Azure, MinIO, they all support it. And so Ceph supports it. And so really AWS as the biggest and most popular object store was the last holdout, and it was ridiculous that they didn't support it, and now they do. So we feel really comfortable relying on it. I would mention that, you know, you can live without it if you're willing to accept some sort of trade-off on just how robust you need the commit process to be. You know, if you can guarantee you're not going to try to create a race condition and can live with spacing your commits by several seconds or something like that, you're never even going to come up against that need. So, but yeah, all of the major public cloud providers support it, and so we feel that it's something that we can depend on. Go ahead, Alden.
This is awesome. Thank you, guys. This is really cool. Thank you all for doing this. I'm curious about what it looks like to write to a Icechunk store with multiple processes or multiple clients at the same time. How do you think about that? What do you do it?
That's a great question, and I'm actually going to pull up an Icechunk issue where we talk about how to support that, because I made a figure that I can use to answer your question really well. So the short answer is this is one of the trade-offs of using Icechunk, is that distributed rights are a little more complicated. They're still possible, but they're more complicated. So here's how a distributed right works with regular Zarr today. So I've tried to make this fancy diagram. Basically, each worker just stores its data into object storage, and you know, it stores its chunks when it's done, and there's no problem. Never has to do it. The state about those chunks is recorded in the object store. With Icechunk, you need to keep track of some metadata from each write that happens and gather it back to the client. And then that client needs to commit the snapshot when those writes are done. And so if you can orchestrate this, it's very well supported to do a distributed write. And we have done distributed writes using multiprocessing and using Dask, but you have to sort of orchestrate it manually. You have to define those tasks, and you essentially have to plan your write not as a map operation, but as a map reduce, where you gather back those pieces of metadata after each worker is done. Today, this doesn't work with Dask distributed. So if you want to write to Icechunk data using the Dask array, sorry, I should be clear, Dask array doesn't work with Dask distributed. So if you want to write Dask arrays in distributed mode using Icechunk, this still needs to be solved. And this is something that we are actively working on. If you just want to use multi-threading, though, on a single big machine, it already works today and actually is really fast and performant. So for many cases, that is good enough. But yeah, it's definitely something that's on the roadmap that we're going to have to deal with.
Cool. Thank you. That's helpful.
Folks, this has been awesome. It's been really great to see the response to Icechunk. We can clearly see folks are enthusiastic about it. I want to thank our Earthmover team, in particular Sebastian Gauken, who led a lot of the design of this project. Should have mentioned that up front. Please go star the repo. It's great to have that number go up. let's see. I saw, did someone have another question? I think we should wrap up now. So please feel free to email me, reach out on GitHub if you have more questions about Icechunk. We welcome your contributions, and we're super excited about this, and looking forward to seeing you all around on the internet.